Hello and welcome to Unit 4 on Conservation of Energy. In this video we are going to be starting Lesson 4 on elastic potential energy and energy conversions. And along with that, largely what we're going to be dealing with is springs. So springs have a couple unique formulas. Nothing too complicated, I wouldn't say. But there are two that I'm going to introduce before we get into this first example problem. We're going to actually need both of these formulas in the example problem. So first, if we want to do a little bit of a flashback into dynamics, we're going to just be dealing with the force of a spring. And the formula for force of a spring is, well, force of a spring with a subscript s is equal to negative kx. And so what these values stand for is, well, force naturally is the force of that spring, but the k value, k is for the stiffness of the spring. So stiffness. And it has a set of units in newtons per meter. And quite literally, the k value and the stiffness of this is how many newtons of force is required to move this spring to either stretch or compress. An ideal spring will take the same amount of force to squish as it does to stretch it. Anyways, that much force to move it a particular distance. So let's say it took 10 newtons to stretch a spring 1 meter. That spring would have a k value of 10 newtons per meter. All right. Next we have this x value. And this x value is the displacement value. It's how far we're stretching the spring, which makes sense. If this is newtons divided by meters, we're going to be multiplying it by meters to get newtons. So this is just how far we stretch the spring. How far we stretch it. Or squish it, right? Because springs we can stretch or squish. All right, so that's one of them out of the way. I'm going to put that one away. So I think it's faster just to erase this thing. And let's bring out the other one. Next we have energy of a spring. This is going to be the energy stored in that spring if we squish it or stretch it out. And then, you know how springs like to spring? Well, this is 1/2 k, and we know k, that's our stiffness, times x, which is our distance, but x is squared. This looks very similar to our kinetic energy formula, right? Except it's not mass times velocity squared, it's 1/2 kx squared. All right. With that said, I think we are prepared to jump into this first example problem. So, we have I have one more thing to mention. And this question is perfect for demonstrating it. The x value, the value of the distance that this spring gets stretched. Springs ideally are massless. It makes the math much easier for us. I know everything's going to have mass. Later on in your journey of physics, if you continue on with it, you will be getting situations where the spring is probably no longer massless, and that's going to be a factor. But to keep things simple at the beginning, springs are massless. Okay. Anyways, x value is what I was getting to. We measure from a spring's relaxed state. So there's nothing hanging on this spring other than itself. This spring is relaxed. It's at equilibrium. It likes to be here. All right. When we add a weight to it, it's going to stretch out. This weight is stretching this object out. So our x value is this difference in distance from the relaxed state to the stretched state. We could also compress this spring, and this could also be considered an x value when we squish it down from the relaxed state. Okay, So x is sorted out. I think we are good to go here. I'm also going to put this formula away. It will be coming back later, but I don't think we quite need it yet, because we're getting to the question. A 500 gram mass is suspended from a vertical spring. That's what I have here, relaxed state, and then add the mass and it stretches out. So before, after. Determine the elastic energy stored in the spring by taking measurements from the diagram. So that is a little bit different. I'll give you the measurements that I have in my diagram. You can solve the problem on your own using the same steps, but based on what print of the booklet that you have, you are likely going to have, a photo of a different size. I have a fairly old version of this workbook. Okay, so what do I want to add on here now? Well, ultimately, we want to determine the elastic energy stored in the spring. So maybe I shouldn't have taken that formula down. We want elastic spring energy. So that's equal to 1/2 kx squared. And using our rulers or some sort of measuring device, we can determine that our rest length, at least for me in my print, this is 18 millimeters. And this length, the stretched length, works out to 28 millimeters, which leaves us with an x value here of 10 millimeters, not 10 meters, there, 10 millimeters. Okay, so we have x. That's good to go. But the spring constant we don't have. And how do we go about calculating that spring constant? Well, we're going to have to use some dynamics. I'm sorry. But it's not going to be too bad. Jump back into blue here. This spring, this situation, this is the one we're going to be looking at. It doesn't move, right? So we could say that force net, I'm going to move this down a little bit, force net is equal to 0, because it's not moving, it's not accelerating. And force net is equal to the sum of all of our forces. So force net is equal to, pulling upwards, we've got force of the spring, and pulling downwards, we've got force of gravity. Alright. If we rearrange this now, we end up getting 0 is equal to force of spring plus force of gravity. And so really, we could say that force spring, which is, negative, I'll write it all out. 0 is equal to negative kx plus mg. So rearrange, k times x is equal to m times g. Now we have the displacement. We've got mass and we know g. So we can just rearrange and solve for k. If I went through that quick and you got a little bit lost, go back and rewatch it. It is actually quite a straightforward little dynamics trick, but it might take a couple times to get through that. Alright, so we end up with k is equal to mass times gravity over x. Plug in some numbers here. This is 0.5 kilos times 9.81 meters per second squared, all divided by 10 millimeters, which is 1 centimeter, which is 0.01 meter. So we get a k value of, what do I have here? 490. Now, my work is a little bit messy. I believe, I better punch this in to be sure. I don't know if it's 490.5 or 4,900. So we have 0.5 times 9.81 divided by 0.01, and it is 490.5. Good. And that is in newtons per meter. So it takes 490.5 newtons to stretch or to compress this spring 1 meter. Alright, now we have K. We have all of our values. We can finish this question off quite easily. Let's switch into red and say energy of a spring is equal to 1/2 times our new value here, 490.5 newtons per meter, times our x squared, so 0.01 meters all squared. So energy of a spring is equal to, I better also punch that one in, because, well, we'll see. 0.01 squared times 490.5 divided by 2 works out to 2.45 times 10 to the negative 2 joules. So 2.45 times 10 to the negative 2 joules. And that's it. So there was a little bit of measuring in this question, a little bit of dynamics work in order to figure out K, but ultimately if you stick to your formulas and you know your foundations, you should be able to start piecing these multi-part questions together. Alright, that's all.